Hey everybody. I wanted to add some more content on the discrete probability density functions. I've had two or three students contact me and say they were confused, and that's fine. We haven't gone into detail on these, so let's dig a little deeper. And and one of the problems that has been specified by these students is, they don't know which probability distribution applies in which situations. I want to focus you on two ideas, right? So I want to focus you on what's the stopping criteria for the probability scenario? Is there a fixed number of draws, or is there a possibly infinitely many draws that could happen? And then the probabilities themselves could either be fixed or changing. And based on these criteria, we're going to narrow down which probability distributions could be in play. Help us make the right choice, right? So again, we're talking about the binomial, geometric, the hypergeometric, and the negative binomial distributions. And what I mean by the stopping criteria, think about the geometric distribution. At least in theory, we could have infinitely many repetitions, right? So say you have a 20% chance of success. And we can see that, yes, though it's unlikely, we could have 10 or 20 or 100 failures in a row before the first success. It doesn't really have a stopping criteria until the success occurs. And we don't know where that success is going to occur. So that's what I mean by theoretically infinite. Of course, it's very unlikely, very, 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 very unlikely that we're going to have 100 trials with no successes. But it's possible. Okay, so possibly infinite is what I mean, or theoretically infinite. Right, and so then let's take a look, because we can make a chart of our four discrete probability density functions, right? And we can see, oh, two of them have a fixed number of trials, the binomial and the geometric. And two of them, geometric and negative binomial, have a possibly infinite number of trials. And both of them have a stopping criteria of k successes. Now, for geometric, it's exactly one success. And for negative binomial, it might be three successes, or when the fifth success occurs, we're stopping, right? And it turns out that the geometric distribution is just a subcase of the negative binomial distribution where k equals 1. But they both have this theoretically infinite number of trials that could happen, right? And like we said, that 20% probability of success, that that situation could occur over and over and over with no successes. It could go forever, possibly. All right, and then the probabilities. Now, three of these have a fixed probability of success. The only one that doesn't is hypergeometric. And what's hypergeometric? Well, that has to do with the partitions, right? So if I have the deck of 52 cards and I have 13 hearts and 39 other cards, well, the probabilities change because after I've picked a heart, there's no longer 13 out of 52. There's only 12 out of 51 because there's fewer cards left overall, and there's fewer of the heart suit left, right? So that's what I mean by the variable probability of success. So if the draws are happening without replacement, then those probabilities are changing slightly after every draw. Okay, so got some examples here and want to go over these with you. Let's first go through these. The main idea is we have an M&M factory and we have different production lines feeding into this collection batch, and each production line is monocolored. It makes a single color of candy, and then they pour into this big collection area, and that's where the colors get mixed, okay? So we have the probabilities for the next hour or so. We know that the probabilities are going to be 50% of the time the batch will be red that gets dumped in, and 30% of the time the batch that gets dumped in will be green, and 20% of the time the batch that gets dumped in will be yellow, okay? So what is the probability, right, that exactly 4 green or yellow batches occur before the third red batch? Okay, well, the probabilities aren't changing, right? We still have the 50, 30, 20% up here. So the probabilities are fixed. So we know it's not hypergeometric, right? But here we have a stopping criteria of what? The third red batch. This is k equals 3. We have the third success is the stopping criteria. Therefore, we have the negative binomial, right? I can tell that we have the negative binomial because of this stopping criteria. It could have been geometric if they asked when the first red batch would occur, but since they said, hey, when's the third red batch going to occur, I know that that's negative binomial. And we're going to go through and actually put some more, we're going to do some calculations, actually find these probabilities in just a second, but let's look at this next one. Mandy is selecting 15 M&Ms with her eyes closed. Look, that's a fixed number of trials. Okay, so it's either got to be binomial or hypergeometric. I know that. Why? Because there's 15 trials. It's finite. There's a specified finite number. And then, what is the probability she selects 10 red candies? Okay, well, notice that we've got a batch of 30 red and 70 green candies. And when she takes a red candy, then there's only 29 of them, right? So this is the hypergeometric. This is the changing probabilities, right? That's what I was trying to point out, that these probabilities change, not much, but they change a little bit as I start selecting candies, or as Mandy starts selecting candies. So we have changing probabilities, fixed number of trials. That's hypergeometric. What is the probability that 6 of the next 10 batches are green? So we're back up in this situation. Okay, 6 of the next 10 batches are green. Probabilities are fixed and a fixed number of trials. Okay, so again, either hypergeometric or binomial. And then what is it? The probabilities aren't changing. Wait, I said if the probabilities are fixed, right, the only one it can't be is hypergeometric. But there's a fixed number of trials. That stopping criteria rules out geometric and hypergeometric, right? So the only thing this one can be, right, is binomial. 6 of the next 10 is the binomial. All right, and let's keep going. What is the probability that the first yellow batch occurs on the 10th batch? Fixed probabilities, they don't change. And it's a fixed number of trials. Is it? Well, we're specifying the 10th batch, but the stopping criteria is the first yellow batch. And theoretically, the first yellow batch could happen on the first trial, the third trial, the 30th trial, or infinitely many, right? So it turns out that even though I have this ostensibly finite repetition, it could be infinite. In fact, it doesn't, the first yellow batch doesn't have to occur on the 10th or the 20th or in the first 30 at all, okay? So what does that mean? That means that we have a fixed probability of success and we have k equals 1. This is geometric, right? We're going to keep going with that geometric pattern until the first yellow batch occurs. Excellent. And then what is the probability that of the next 15 batches, 3 of them are green? Well, you'll notice that it looks a whole lot like this one. Why? Well, it's got a fixed probability of success and it's got a finite number of trials, right? This isn't there's no criteria that stops us at 15. It's just we do 15 and we stop. Therefore, this is binomial, okay? And then the fourth red batch occurs on the 9th batch. Again, we have a k equals 4 stopping criteria that doesn't have to be met, right? Theoretically, we could go a long time before the fourth red batch actually occurs. So the option 6 here is negative binomial. Okay, so I created a notebook so we can go over these in a bit more detail. What is the probability that exactly 4 green or yellow batches occur before the third red batch? So let me just put in, what do we need? We need 6 slots and then a success to finish, right? The 7th one has to be a success. And that means that there are a couple of other successes in here somewhere. We don't know where, right? But so we're distributing two successes, right, amongst the first six slots. So right, so our probability here is going to be, let me do probability equals, and we're going to do combinations, right? So we're going to have to do combin, and we're doing six choose two right out of the six slots. We're gonna sprinkle in those two successes, right, times the probability of success. Um, so the red batches are 50%, and we have to have three successes. So the exponent there is 3, and then the probability of failure is also 0.5. And there are 4 failures. And I'm going to pause the video because I did not put in a combinations line up here. So I'm going to have to do that quickly and come back to you. Okay, and I'm back, and you can see that I now have the combination and permutation cell that defines those. I went and got those off the course notes website. And now this is an error. Let me throw in some hashtags to comment that one so it'll run. And then the probability. Oh, I'm throwing in a backslash there. That's a different programming language. And I did not specify, hey, print out what you think the probability is. And there we go. The probability is about a little less than 12%, a little 11.7%. Okay. So again, this is negative binomial. Why? Well, because I have a k equals 3 success criteria. When I have the third success, the third red batch, then we stop. Okay, so when we're selecting 15 M&Ms with Mandy's eye closed, again, I know there's a finite number of trials, but because she's drawing from a specified number of candies, the probabilities are going to change, right? So fixed number of success with the probabilities variable, that's hypergeometric. So that probability is going to be hypergeometric, right? So 30 choose 10, right? So, sorry, I didn't get that quite right. Out of a batch of 30 red, she's going to draw 10. That's the success. And then from the 70 that are failures, she's going to draw the remaining 5, right? So this hypergeometric. And I'm sorry, I calculated the number of ways to select 10 candies, right? So we get this huge integer. Okay. The probability is what? Well, she's drawing, the total number of possible draws is she's drawing from 100 candies, and she's drawing 10. So that's the total of number of ways she can draw candies. And then the numerator is the total number of successes. And we get a probability that does make sense now, 0.143, excuse me, 0.144%. Okay, what is the probability that the six of the next 10 batches are green? Notice that we have a finite number of trials, a specified and finite number of trials, and we have the success criteria. Okay, and I've got to remember what the green was 30%. So the success criteria is now 30% chance, right? 6 of the next 10 batches are green. So what am I doing here? My probability is going to be, I have to sprinkle 5 successes among the first 9 slots so that the 10th slot can be a success, right? So I'm going to do combin 9, choose 5. 9 slots, choose 5 successes. Okay. And then what do I have? I have 6 successes, right? So I take my probability of success, which was 0.3, and I raise it to the 6th power. And then my probability of failure and raise it to 4, right? Because if 6 out of 10 batches are green, there we go. Wait, and I'm apologizing because I'm doing it like this is the negative binomial, and it's not. It's the binomial. Okay. So what are we doing? We're doing 10 out of 10 slots, any 6 of them can be green. Okay, and so I'm sorry, I'm switching now from negative binomial to actual binomial, which is the correct way to do this, and my apologies there. Okay. Um, so for number 4, what is this is geometric, right? The first yellow batch occurs. This is k equals 1 successes, fixed probabilities. The yellow batches are 20%. So what are we doing here? There's no combinations, right? Why? Because the probability is just going to be 9 failures, so that's going to be 0.8 raised to the ninth times the number of successes, which is 1 success, ends this. So I'm not going to put, I mean, you can put the to the first power in it, and you can see that the exponents add up to 10. Why? Because there's 10 trials, right? So I have 9 failures and then a success. So the probability is equal to about 2.5%, right? 2.68%. Then, what is the probability that of the next 15 batches, 3 of them are green? Okay, this is binomial again. Why? We have a fixed number of trials, right? So it can't be geometric or negative binomial. Fixed number of trials, fixed probabilities, so it can't be hypergeometric. So this is binomial. And so what are we doing? We're doing the probability equals 15, choose 3, times the probability of success, which is 0.3, times the number of successes power, there are 3 successes, times the failure probability raised to the number of failures power. I'm sorry, 15 batches, so that's not 7, it's 12. I thought I was thinking there were 10 trials, but there's 15 trials. 12 of them are failures, so 0.7 to the 12. 3 of them are successes, so 0.3 to the third. And then 15 choose 3. Why? Because there are 15 trials and 3 successes, but we don't know where the successes occur. We could have the first one be a success, the last one be a success, the middle 3 be a success. So with that uncertainty, we just do the 15 choose 3 to to rearrange the 3 successes into the 15 slots in all the possible ways. And we have about a 17% chance that of the next 15 batches, 3 of them are green. And then what is the probability that the 4th red batch occurs on the 9th batch? Again, we have the first 3 red batches have to occur in the first 8 slots, right? So the probability is going to be equal to comban 8 choose 3, right? And how many successes occur? And these are red batches, so you'll see there's a shortcut, right? Since the probability of success is 1/2 and the probability of failure is 1/2, so I don't have to split these up. I'm splitting them up in good form, right? Because there are 4 successes. So it raised the probability of success to the number of successes power, and the probability of failure to the number of failures power. But you can see they're both the same. So I could have done 0.5 raised to the 9th if I really wanted to go fast, go quickly. And the probability is about 11%. Okay, so I wanted to go back over these and show you how I'm using the criteria, the stopping criteria, and how the probabilities work to try to narrow down which item it could be, whether it's binomial, negative binomial, geometric, or hypergeometric. The decision making I'm doing is looking at how the probabilities work in the stopping criteria, narrowing that down, and then trying to fit the pattern. And once you do that, I think you'll find it a lot easier to figure out which of the 4 discrete probability distributions that we're supposed to use on a given problem. All right, wanted to get you this information out before the test. Good luck studying this, and good luck on the test.